Everything you think you know about the universe might be completely wrong. We are about to explore 25 cosmic phenomena that challenge the very fabric of reality, from ghostly dark matter to the possibility we live in a simulation. By the end, your perception of existence itself will be fundamentally altered. Why do stars move as if pulled by an invisible hand? And could the entire cosmos be a fleeting illusion? What single cosmic mystery makes you question what is real galaxies spin with such ferocious speed that they should tear themselves apart, scattering their stars into the endless dark? Yet they hold together, bound by an invisible hand. This is the profound mystery of dark matter, a substance that defies our most fundamental senses. It does not glow, it does not cast a shadow, and it refuses to interact with light in any way. We only know it is there because of the gravitational grip it exerts on everything we can see. The story begins nearly a century ago with an astronomer named Fritz Zwicky, who noticed that entire clusters of galaxies were moving in ways that made no sense. There simply was not enough visible stuff to hold them together. He called this missing mass dark matter, and the name stuck. Decades later, the brilliant Vera Rubin provided the definitive evidence. By meticulously charting the rotation of spiral galaxies, she found that stars at the outer edges moved just as fast as those near the center. According to the laws of gravity, these far-out stars should have been flung loose, like water droplets from a spinning bicycle wheel. They were not. Something unseen was holding them in place, a vast, massive halo enveloping each galaxy. The evidence only grew stronger. We see dark matter's handiwork through gravitational lensing, where the fabric of spacetime itself is warped by immense mass, bending light from distant galaxies like a funhouse mirror. We detect its faint imprint on the cosmic microwave background, the afterglow of the Big Bang. Perhaps the most stunning proof came from the Bullet Cluster, a cosmic car crash of two galaxy clusters. When they collided, the clouds of normal gas, the visible matter, slammed together and slowed down, but the dark matter, which does not interact, sailed right through. Telescopes showed that most of the mass was not where the visible gas was. It was somewhere else entirely, a ghostly presence mapped by its gravity alone. How does something we cannot see dictate the structure and fate of the entire cosmos? This invisible architecture, making up 27% of the universe, forces us to admit that what we call reality is built upon a foundation we are completely blind to. Just as we grapple with the universe's invisible anchor, we must also confront its phantom engine. The cosmos is not merely expanding, it is accelerating, flying apart at a rate that grows faster with every passing moment. This is the confounding reality of dark energy. In the late 1990s, two independent teams of astronomers were observing distant stellar explosions known as Type 1, a supernova. They were using these cosmic beacons to measure the expansion rate of the universe, expecting to find that the pull of gravity was slowing it down. Instead, they discovered the exact opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than anyone had predicted. The universe's expansion was not slowing, it was speeding up. This revelation was so profound it earned the researchers the Nobel Prize in Physics. The force behind this great cosmic push is dark energy, a term that describes our profound ignorance. It constitutes a staggering 68% of the entire cosmos, dwarfing both dark matter and the ordinary matter that makes up our world. Albert Einstein himself had flirted with a similar idea a century earlier. He introduced a fudge factor into his equations of general relativity called the cosmological constant. a sort of anti-gravity force needed to keep a static universe from collapsing under its own weight. He later called it his greatest blunder after the expansion of the universe was discovered. Yet now, it seems he may have been right for the wrong reason. What could this dark energy be? One leading theory suggests it is the energy inherent to the vacuum of space itself. Empty space is not truly empty, but seethes with virtual particles that constantly flicker in and out of existence. This quantum fizz could generate a repulsive force. Another idea proposes a dynamic energy field that permeates the cosmos, nicknamed quintessence, which could change over time. As leading cosmologist Dr. Adam Rees puts it, dark energy is the dominant component of the universe, yet we know almost nothing about it. We see its effects etched across the cosmos. Data from the Planck satellite and massive galaxy surveys map how this energy shapes the vast cosmic web, stretching the fabric of space-time and determining the ultimate fate of everything. If this acceleration continues unchecked, a chilling future awaits. Distant galaxies will be pushed away faster than the speed of light, their light forever unable to reach us. Over trillions of years, the observable universe will shrink to a mere ghost of its former self, leaving any future civilization with a sky nearly devoid of galaxies, a lonely and isolated existence. This mysterious pressure, working against gravity on the grandest scales, forces us to wonder what other fundamental forces are hiding in the darkness, silently shaping our reality. But this phantom acceleration is not the only unseen force guiding our cosmic journey. Our entire galaxy, the Milky Way, is caught in a relentless river of gravity, flowing toward a mysterious and unseen region of space known as the Great Attractor. Picture our home, a swirling disk of hundreds of billions of stars, being pulled through the void at a staggering 2 million miles per hour. This is not a random drift, it is a purposeful motion, a cosmic current we cannot resist. The discovery of this motion came from studies of what astronomers call peculiar velocities, the way galaxies move that cannot be explained by the universe's general expansion. In the 1970s, scientists mapping these motions found a puzzling consensus. An immense volume of space, including our own local group of galaxies, was all streaming in the same direction, toward a point in the constellation Centaurus. The problem was when they looked there with optical telescopes, they saw almost nothing. The Great Attractor lies directly behind the plane of our own Milky Way, in a region so choked with cosmic gas and dust that it is known as the zone of avoidance. It is like trying to see a distant city through a dense, permanent fog. As astronomer Dr. Alan Dressler famously described, it is like finding a hidden mountain range behind a fog bank. We knew the mountain was there by its gravitational pull, but we were blind to its peaks. To pierce this veil, astronomers turn to telescopes that see in other wavelengths, like infrared and radio waves, which can pass through the obscuring dust. What they revealed was an immense concentration of mass, a massive overdensity of thousands of galaxies all clustered together, whose collective gravity creates this powerful cosmic tug. This discovery fundamentally reshaped our understanding of our place in the cosmos. We now know that the Great Attractor is not the final destination, but merely the central gravitational anchor of a structure far grander than anyone had imagined, the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is a cosmic filament containing over 100,000 galaxies, all flowing along shared rivers of gravity toward this central point. Our Milky Way is just a single suburb in this vast metropolitan web. What other colossal structures, even larger than Laniakea, remain hidden from our current view, their gravity silently steering the motion of entire superclusters? This constant, unseen motion reminds us that we are not still observers in the universe, but passengers on a grand and invisible journey, pulled by forces we are only beginning to map. This relentless cosmic pull is mirrored by a connection so intimate it defies the very nature of space and time. Two particles can be linked in such a way that measuring one instantly influences the other, even if they are on opposite sides of the galaxy. Albert Einstein famously rejected this idea, calling it spooky action at a distance, a phrase that perfectly captures its unsettling nature. This is quantum entanglement, a cornerstone of quantum mechanics that challenges our most basic assumptions about reality. The phenomenon begins with superposition, the bizarre ability of a tiny particle to exist in multiple states at once, like a spinning coin that is both heads and tails simultaneously. When two particles become entangled, their fates are permanently intertwined. They are described by a single quantum state, the act of measuring one particle, of forcing that spinning coin to land on heads, instantly forces its partner to land on the corresponding state, tails, no matter the distance between them. For decades, this was a philosophical debate. Then physicist John Stuart Bell devised a mathematical test, now known as Bell's inequalities, to prove whether this spooky action was real or if some hidden classical variable was at play. Experiment after experiment has confirmed it. The correlations between entangled particles are stronger than any classical physics could allow. Physicist Dr. Anton Zeilinger and his team have pushed these experiments to incredible lengths, demonstrating entanglement over hundreds of kilometers and even using it for quantum teleportation, where the quantum state of a particle is instantly transferred to another distant particle. This is not science fiction teleportation of people or objects, but the transfer of information, a profound step forward. This strange connection is not just a laboratory curiosity, it is the engine of a technological revolution. Quantum cryptography uses entangled particles to create communication channels that are fundamentally unhackable, because any attempt to eavesdrop on the particles immediately disturbs their fragile state and reveals the intrusion. Quantum computers leverage entanglement to perform calculations that would take today's most powerful supercomputers millions of years, promising to unlock new frontiers in medicine and materials science. But how can information seem to travel faster than light, seemingly violating Einstein's theory of relativity? The key is that no useful information is actually transmitted. You cannot send a message this way because the outcome of your measurement on your end is random. You only know what your partner has when you compare notes through a conventional, slower-than-light channel. The spooky action is a correlation, not a communication, yet it forces us to confront a startling possibility that at its most fundamental level, the universe may not be composed of separate, isolated objects, but is a deeply interconnected whole where the concepts of here and there are not as absolute as they seem. What other invisible threads bind the cosmos together, weaving a tapestry of connection we are only beginning to perceive? This deep interconnectedness suggests reality is not what it seems, a notion tested to its absolute limit by black holes. At their edge, the event horizon, lies a paradox that threatens to unravel physics itself. The problem begins with something seemingly simple, an object falling in. From our perspective outside, the object appears to slow down, its light red shifting into oblivion until it seems to freeze at the horizon, never quite crossing. But for the object itself, it crosses that boundary without incident, pulled toward the central singularity. This creates a fundamental conflict. According to the rules of quantum mechanics, information cannot be destroyed. The exact quantum state of every particle that made up that object, its unique identity, must be preserved forever. Yet if the object is irretrievably lost inside the black hole, that information appears to be permanently erased. The genius Stephen Hawking deepened this mystery with his discovery of Hawking radiation. He realized that black holes are not completely black. Due to quantum fluctuations at the very edge of the event horizon, pairs of virtual particles constantly pop into existence. Normally, these particles annihilate each other instantly, but if one particle falls into the black hole while its partner escapes, the black hole loses a tiny amount of mass. Over unimaginable eons, a black hole can evaporate completely through this process. This leads to the terrifying core of the paradox. If the black hole evaporates and vanishes, what happened to all the information about every star, planet, and atom that ever fell into it? Was it truly destroyed, violating a sacred principle of quantum theory? Or is it somehow encoded in the Hawking radiation, which itself appears to be random and featureless? This is the black hole information paradox. The physics community has been wrestling with it for decades. One profound solution comes from the holographic principle, championed by theorists like Dr. Leonard Susskind. This idea suggests that all the information about what falls into a three-dimensional black hole is not lost inside, but is instead perfectly preserved as a kind of quantum code on its two-dimensional surface, the event horizon. It is like a cosmic DVD where a three-dimensional movie is stored on a flat, two-dimensional disk. The information is not destroyed, it is just translated. This leads to other radical ideas like the firewall hypothesis. If information is stored on the horizon, then the point of crossing might not be the smooth spacetime Einstein predicted. Instead, it could be a searing wall of high-energy particles, incinerating anything that attempts to pass through. This would resolve the information paradox, but at the cost of violating general relativity's core tenet. Recent advances in string theory and new mathematical tools are providing fresh pathways to a solution, suggesting that spacetime itself may not be a fundamental stage but an emergent property, a tapestry woven from vast networks of entangled quantum bits. The fate of a single bit of information falling into a black hole forces us to question the very nature of existence. Is our three-dimensional reality just a projection from a deeper, two-dimensional reality at the universe's edge? What happens to the identity of what falls in may hold the key to understanding what reality truly is, a question that draws us toward the black hole's most bizarre and silent inhabitant. While the fate of information inside a black hole remains a fiery debate, what if there is a theoretical exit? Picture a black hole running in reverse, a cosmic fountain that violently expels matter and energy into the universe while refusing to let anything back in. This is the hypothetical white hole, a region of spacetime that is the exact mathematical opposite of its dark cousin. White holes are not just science fiction, they are valid, if highly speculative, solutions to Einstein's own equations of general relativity. In the complex geometry of the maximally extended Schwarzschild solution, which describes a perfectly symmetrical, non-rotating black hole, the mathematics naturally suggests the existence of a white hole on the other side of the bridge. This bridge is the famous Einstein-Rosen bridge, more commonly known as a wormhole. In this model, the black hole is the entrance and the white hole is the exit. The renowned cosmologist Dr. Carlo Rovelli and his colleagues in loop quantum gravity have taken this idea even further. They propose that the immense gravitational collapse that forms a black hole could eventually rebound due to quantum effects. Instead of crushing down into a singularity forever, the collapsing matter would hit a quantum wall and bounce back, transforming the black hole into a white hole. This process would not be instantaneous, of course. For a black hole with the mass of our Sun, the transformation would take billions of times the current age of the universe to occur. But for smaller, primordial black holes forged in the Big Bang, the transition could be happening right now. This leads to a fascinating and explosive possibility. What if the most powerful, mysterious blasts of energy we see in the cosmos, the incredibly bright gamma ray bursts that outshine entire galaxies for a few moments, are not the birth cries of black holes, but the final death throes of tiny white holes? These white holes would be inherently unstable. Unlike a black hole's relentless pull, a white hole's nature is to repel. Any matter or energy falling onto it would add to its mass, and according to general relativity, this would cause it to collapse instantly back into a black hole. This means a classical white hole, if it ever formed, would be a spectacularly short-lived event. Perhaps the most profound idea connects white holes to the very beginning of everything. Could our entire universe be the result of a white hole eruption from a parent cosmos? In this mind-bending scenario, the Big Bang was not a singularity from nothing, but the violent output of a white hole in a larger, pre-existing reality. We would be living inside the expelled debris. This offers an alternative origin story, one of an eternal cycle of cosmic rebirth rather than a single creation event. While there is no observational evidence for white holes, their theoretical existence forces us to stretch our imagination to its absolute limit, revealing a cosmos where every entrance might have an exit, and every ending could be a new beginning in disguise. The profound silence of the cosmos is perhaps its most deafening message. With hundreds of billions of stars in our galaxy alone, and many of those stars hosting Earth-like planets within their habitable zones, the universe should be teeming with life. Yet our radio telescopes have scanned the heavens for decades and have heard nothing but the natural background hum of the cosmos. This is the Fermi Paradox, a contradiction that challenges our very understanding of life's place in the universe. It all started with a simple lunchtime question. The physicist Enrico Fermi, discussing the high probability of alien civilizations with colleagues, looked up and asked, "Where is everybody?" His point was devastatingly logical. If intelligent life is common and the galaxy is billions of years old, then even at a slow pace of exploration, the entire Milky Way should have been colonized many times over. We should see evidence of alien engineering, hear their broadcasts, or find their artifacts. We see nothing. This silence has spawned a spectrum of possible solutions, some hopeful and others deeply unsettling. The most sobering is the Great Filter hypothesis. This idea suggests that the evolution of life from simple origins to a spacefaring civilization requires passing through a series of critical steps, and one of these steps is almost insurmountably difficult. It could be that the origin of life itself is a cosmic fluke, or perhaps the leap from single-celled organisms to complex multicellular life is the rare event. The most terrifying possibility is that the Great Filter lies in our future. It could be that all advanced civilizations inevitably discover a technology, perhaps nuclear war, artificial intelligence, or something we cannot yet conceive, that leads to their own swift destruction. The silence, then, would be a cemetery quiet. Other theories are less grim but equally mind-bending. Perhaps we live in a galactic zoo, a protected wilderness area where advanced civilizations have agreed to observe us without interference, waiting for us to reach a certain level of maturity before making contact. Or maybe we are simply looking for the wrong things. As the pioneering SETI astronomer Dr. Jill Tarter has long argued, our searches are limited by our own imagination and technology. We have been listening for radio signals for a mere cosmic blink, 100 years out of 13.8 billion. An advanced civilization might have moved far beyond primitive radio, communicating through quantum entanglement or manipulating spacetime itself, their conversations completely invisible to our crude instruments. The Drake equation, a framework for estimating the number of communicative civilizations, lays bare all the variables. We now know that planets are common, filling in one of the equation's great unknowns. But the other factors remain profound mysteries. What fraction of those planets actually develop life? How often does life evolve intelligence? And most crucially, how long does a technological civilization last? If the average lifespan is only a few hundred years before it self-destructs or transcends, then the galaxy may be filled with the ghosts of civilizations that flashed into existence and vanished before we ever tuned our telescopes to the sky. This cosmic silence forces us to confront an existential choice. Are we a fluke, a lonely spark of consciousness in an immense and empty void? Or are we simply a very young species, listening for whispers in a cathedral where everyone else is singing in a language we have not yet learned to hear? The answer to this silence may determine whether intelligence is a cosmic dead end or a beginning, a question that makes the search for any signal, any sign at all, one of the most important endeavors we can undertake. That same cosmic silence is occasionally and violently shattered by a signal of almost unimaginable power. A flash of radio energy from the depths of space compresses more energy than our sun, emits over 80 days into a single millisecond blast. These are fast radio bursts, or FRB, and they are one of the most electrifying and perplexing discoveries in modern astronomy. The story began in 2007, when astronomer Dr. Duncan Lorimer and his student were sifting through archived data from the Parkes radio telescope in Australia. They found a spike, a burst so intense and so brief that it had been overlooked for years, a cosmic ghost hiding in plain sight. For a long time, it was a solitary mystery, a one-off event that left scientists baffled. Was it a local glitch, some unknown form of terrestrial interference? Or was it truly a message from the distant cosmos? The mystery only deepened when more of these bursts were found. Then came the real game changer, the discovery of a repeater. A source designated FRB 1211-2 began firing off multiple bursts, not just once, but again and again, sporadically from the same patch of sky. This proved definitively that at least some of these events were not cataclysmic one-off explosions, but were generated by a source that could survive the immense energy release and do it repeatedly. How do you track down such an elusive target? Astronomers use a clever clue embedded in the signal itself, called the dispersion measure. As the radio waves travel across millions of light years, they pass through the sparse clouds of electrons in intergalactic space. This cosmic fog delays lower-frequency radio waves more than higher-frequency ones, causing the signal to smear out. By measuring this smearing, astronomers can calculate how much material the signal has passed through, essentially mapping its long journey to Earth. This is how they traced the repeater FRB 1211-2 back to its home, a tiny, turbulent dwarf galaxy over 3 billion light-years away. This localization was a monumental achievement, but it provided more questions than answers. What inside a small, unremarkable galaxy could be producing such titanic blasts? The leading theories are almost as wild as the bursts themselves. They could be the death cries of ultramagnetic neutron stars, known as magnetars, experiencing starquakes that crack their crusts and release colossal magnetic energy. They might be the product of mergers, like two neutron stars colliding to form a black hole in a final, brilliant flash. Or, and this is where the line between science and speculation blurs, could they possibly be evidence of advanced technology? Some have theorized about powerful interstellar beacons or even the signatures of immense light sails, propelled by focused energy beams across the galaxy. The very brevity and power of these signals challenge the limits of known physics. What natural engine can turn on and off with such ferocious speed and efficiency? Each new detection, especially from powerful new telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, adds another piece to the puzzle, yet the full picture remains stubbornly out of focus. These millisecond cosmic screams remind us that the universe is filled with transient, violent events we are only beginning to notice, flashes in the dark that hint at processes and powers beyond our current imagination. While the cosmos screams with fleeting radio bursts, it has also whispered a single, perfect word. In the quiet of an August evening in 1977, a radio telescope known as the Big Ear was silently scanning the sky, its data printing out as a string of letters and numbers. An astronomer named Dr. Jerry Amon was volunteering his time, reviewing the reams of paper by hand days later. His eyes scanned across a sequence that made him stop cold. The signal was so powerful, so perfectly tuned, that he circled it in red pen and wrote a single, heartfelt exclamation in the margin: "Wow." The wow signal, as it became known, was a 72-second burst of intense, narrowband radio waves, precisely at the frequency of 1420 MHz. This is no random number. It sits right in the protected band where earthly interference is forbidden. And more importantly, it is very close to the hydrogen line, the natural frequency emitted by the most common element in the universe. Any advanced civilization looking to signal its existence would know that this is a universal channel, a logical place to call. The signal rose and fell in a perfect curve, matching exactly what you would expect as the rotation of the Earth carried the Big Ear telescope's beam slowly across a fixed-point source in the sky. It was a perfect candidate for an alien beacon, and then it was gone, despite dozens of dedicated searches over the decades, using far more sensitive equipment pointed at the same patch of space in the constellation Sagittarius. The signal never repeated. Not once, Dr. Amon himself remained both fascinated and deeply skeptical, spending years trying to find a natural explanation. He and others proposed possibilities, from a secret military transmission to a reflection off a piece of space debris. One recent theory suggested it was the radio emission from the hydrogen clouds of a passing comet, but the comets proposed were not in the right part of the sky at that time. The mystery only deepens with its perfection and its solitude. It was a shout in the cosmic dark that lasted just over a minute, a shout that we heard with a primitive ear, and one we have been straining to hear again ever since. The profound silence that followed is as meaningful as the signal itself. Was it a one-time beacon, a cosmic hello from a civilization that has long since vanished? Or was it a fleeting alignment, a keyhole through which we briefly glimpsed a conversation not meant for us? The wow signal stands as a monument to both the promise and the agony of the search for extraterrestrial intelligence. It proves that we can detect a signal that fits the profile perfectly, a signal that challenges our isolation. But its singular nature reminds us that the universe guards its secrets closely, offering a single, tantalizing clue, and then retreating back into an enigmatic silence, leaving us to wonder if we were ever truly called. A tiny, persistent drift in the depths of space can unravel our most trusted laws. For decades, the twin Pioneer probes, 10 and 11, on their grand tours of the outer solar system, were slowly, inexplicably being pulled back toward the Sun. It was an effect so small you would never notice it on a short journey, a deceleration weaker than a 10 billionth of the gravity we feel on Earth. But across billions of miles of empty space, this minuscule tug added up, creating a navigational drift that stubbornly refused to disappear. This was the Pioneer Anomaly, a ghost in the machine of celestial mechanics that refused to be explained by gravity from known planets, the drag of interstellar dust, or even the gentle push of solar radiation. For a time, it seemed we had witnessed a crack in Newton's and Einstein's laws, a hint of new physics operating in the vast, quiet realms between worlds. The scientific community was captivated. Could this be evidence of dark matter's gravitational pull within our own solar system? Or perhaps a sign that our theory of gravity itself needed a subtle modification at very large scales, an idea known as modified Newtonian dynamics, or MN. The Pioneer Anomaly became a battleground of ideas, a puzzle that pitted the known against the unknown. The real breakthrough came from a meticulous forensic effort led by scientists like Dr. Slava Turyshev. He and his team undertook a monumental task, recovering and reanalyzing decades-old telemetry data from the probes. They built a digital replica of each spacecraft, accounting for every possible source of thrust, no matter how insignificant. The key, it turned out, was heat. The Pioneers were powered by radioactive thermoelectric generators, and these units were constantly emitting heat. The team realized this heat was not radiating away uniformly. A tiny fraction more was bouncing off the back of the spacecraft's large dish antennae than the front. This anisotropic thermal radiation created a photon pressure, an imbalanced push that acted as a constant, very gentle brake, slowing the probes on their journey outward. It was not a new force of nature, but the cumulative effect of countless photons, the very light we see by, giving the spacecraft a nearly imperceptible nudge backward. While this thermal explanation has largely solved the mystery, a whisper of the anomaly persists, a tiny residual drift that some analyses still cannot fully account for. This case is a profound lesson in cosmic humility. It shows us that before we invent new physics, we must exhaustively account for the old. It underscores the incredible precision required for navigating the solar system, where a force 1/1000th of our own gravity can send a probe millions of miles off course over time. What other subtle signals are we missing in the data from other missions, their meaning hidden beneath the mundane glow of a warm spacecraft? This relentless pursuit of a few millimeters per second squared of acceleration prepares us for the next great gravitational mystery, one written not in the paths of probes, but in the very wobble of a distant star. Beyond the gentle drift of wayward probes, the outer solar system holds a deeper gravitational secret. Far past the orbit of Neptune, in the cold, dark realm of the Kuiper belt, a collection of icy worlds is behaving strangely. Their orbits are not random. Instead, they cluster together, their elongated path swinging around the Sun in a coordinated dance that should not be possible by chance alone. These distant objects, with names like Sedna and a handful of other extreme trans-Neptunian objects, follow paths that take them hundreds of times farther from the Sun than Earth. The most peculiar detail is how these orbits are aligned, all pointing in roughly the same direction and tilting in the same way, as if being shepherded by an unseen hand. The mathematics of gravity points to one compelling explanation: the gravitational pull of a massive, undiscovered planet. This is the hypothesis of Planet 9, a ghostly giant lurking in the frozen depths of our own cosmic backyard. The astronomers who first pieced this puzzle together, Dr. Konstantin Batygin and Dr. Mike Brown, used detailed computer simulations to see what kind of object could sculpt these orbits. Their models suggest a planet with a mass roughly 10 times that of Earth, on a wildly elongated orbit that takes it 20 times farther from the Sun than Neptune. At such a distance, it would be incredibly faint, a dark wanderer reflecting only the faintest glimmers of sunlight, which is why it has eluded our telescopes for so long. The hunt is now on, a painstaking astronomical treasure hunt using some of the world's most powerful telescopes, like the Subaru telescope in Hawaii. These instruments must scan enormous areas of the sky, looking for a single, slow-moving pixel of light against a backdrop of millions of stationary stars. It is like searching for a single specific grain of sand on a vast, dark beach. Finding Planet 9 would be more than just adding a new world to our solar system map. It would fundamentally rewrite the story of our solar system's formation. How did such a large planet end up so far away? Was it flung outward in a gravitational tug of war with Jupiter and Saturn in the early days of the solar system? Or is it a rogue planet that was captured by our sun's gravity long ago? Its very existence would force us to reconsider the chaotic processes that built our cosmic neighborhood. This ongoing search reminds us that our exploration of the cosmos is far from over, and some of the greatest discoveries may be hiding in our own celestial backyard, silently shaping the paths of smaller worlds from the shadows. What other ancient relics from the birth of our solar system are waiting to be found in that perpetual twilight? Even mature stars can harbor deep secrets, as one solitary sun over 1,000 light-years away demonstrates with shocking clarity. KIC 8462852, better known as Tabby star, flickers like a faulty light bulb in the cosmic dark. Its light curve, meticulously recorded by NASA's Kepler telescope, is unlike anything else ever seen. While most stars show regular, gentle dips from orbiting planets, Tabby's star plunges into darkness erratically, with its brightness sometimes dropping by an astonishing 22%. This is not the subtle shadow of a planet, which typically blocks less than 1% of a star's light. This is as if a colossal, jagged object were passing in front of it, something massive and uneven enough to obscure nearly a quarter of its face. The discovery was made not by a professional astronomer in a sterile lab, but by citizen scientists, volunteers sifting through public Kepler data as part of the Planet Hunters project. They flagged this bizarre light pattern, setting off a chain of inquiry that would captivate the world. The star's namesake, astronomer Dr. Tabetha Boyajian, led the initial investigation, and her bewilderment was palpable. As she described it, "We had never seen anything like this star. It was really weird." The immediate and most sensational theory was that of an alien megastructure. Could we be witnessing the construction of a Dyson sphere, a vast swarm of energy-collecting panels built by an advanced civilization around their sun? The idea was intoxicating, a potential answer to the Fermi Paradox staring right back at us from the Cygnus constellation. Yet science demands more than exciting speculation. Dr. Boyajian and other researchers spearheaded a massive follow-up campaign, observing the star across every wavelength from radio to infrared. The data told a different story. If solid, opaque objects like megastructures were blocking the light, the star would dim equally at all wavelengths. Instead, the dimming was more pronounced in blue light than in red light. This is the classic signature of dust. Tiny particles smaller than a grain of smoke scatter and block blue light more effectively, just as our own sky appears blue because of how sunlight scatters in our atmosphere. The most likely culprit, then, is a vast, irregular cloud of fine dust orbiting the star in a chaotic swarm. But where did this dust come from? One leading theory suggests a family of exocomets, thousands or even millions of them, breaking up as they swing close to the star, creating a sprawling debris field that intermittently blocks our view. This natural explanation is now favored, but it does not solve every part of the puzzle. Adding to the short-term dips is a long-term mystery. Over the century of historical data, Tabby's star has also shown a significant, steady overall dimming. This slow fading is just as difficult to explain for a star of its age and type. How can a mature star change its brightness so profoundly over such a relatively short time? The very evolution of stars may have a few surprises left for us, with processes we do not yet fully understand. The story of Tabby's star is a triumph of modern astronomy and public engagement, proving that the most curious anomalies can be found by anyone with an internet connection and a sharp eye. It reminds us that while the universe is likely filled with natural wonders we have not yet imagined, the search itself, the process of questioning and observing, is what truly expands our reality. This stellar oddity teaches us to watch the sky carefully, for even a single flicker can challenge everything we thought we knew about the lives of stars. The violence of a stellar death can forge a monster. When a massive star collapses in a supernova, its core can be crushed into a neutron star, a city-sized object so dense a single teaspoon would weigh 1 billion tons. But for a rare few, the transformation goes even further. Their rotation is stolen, their magnetic field wound up to an almost inconceivable intensity. These are magnetars, the universe's ultimate magnets. Their magnetic fields are quadrillions of times stronger than the one that guides our compass. At a distance of just 100,000 miles, the field of a magnetar would be lethal, not through force but through physics. It would warp the very atoms that make up your body, stretching them into thin, useless needles, tearing you apart from the inside out. These cosmic powerhouses were not just theorized, they were discovered through their furious tantrums. In the 1990s, astronomer Dr. Krisa Kuvaliottu and her team were analyzing data from the Compton Gamma Ray Observatory when they noticed something extraordinary. Certain sources were firing off repeated, intense bursts of gamma rays and X-rays, not from the chaos of an explosion, but from a single, pinpoint location in the sky. These were not the death cries of stars, but the seismic shudders of something that was very much alive and under immense strain. The source was a starquake. A magnetar's crust is not a placid surface, but a rigid, crystalline lattice of iron, suspended over a superfluid core. The unimaginably powerful magnetic field trapped inside is under phenomenal pressure, constantly shifting and stressing this stellar shell. Eventually, the crust can no longer take the strain. It cracks. This starquake is a cataclysm on a planetary scale, releasing more energy in a fraction of a second than our Sun will emit in 100,000 years. The proof of their awesome power slammed into our planet on December 27, 2004. A magnetar named SGR 180620, located 50,000 light-years away, unleashed a giant flare. For 0.2 of a second, it outshone the full moon, becoming the brightest object ever observed outside our solar system. The blast of radiation, though from across the galaxy, was so intense it compressed Earth's magnetosphere, ionizing the upper atmosphere and temporarily disrupting long-range radio communications. It was a direct physical touch from a distant, dead star. These events are terrifyingly brief, but they raise a profound question about the limits of nature. What is the absolute maximum strength a magnetic field can achieve? Theorists propose a quantum limit, a point where the magnetic energy becomes so great it would spontaneously create particle-antiparticle pairs and tear itself apart. Yet some observations hint that certain magnetars might be pushing even this ultimate boundary. Their fields so strong they are entering a realm of physics we can only theorize about. They are natural laboratories for states of matter that cannot be recreated on Earth, showing us that the end of a star's life is not a quiet fade, but can be the violent birth of a magnetic phantom. Our own solar system was recently visited by a ghost from a distant star. In October 2017, astronomers at the Pan-STARRS Observatory in Hawaii spotted a faint point of light moving at incredible speed. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. This was the first confirmed interstellar object ever detected, and they named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The data that poured in was baffling. Its brightness changed dramatically as it tumbled, suggesting an extreme, elongated shape, perhaps 10 times longer than it was wide, like a cosmic cigar or a pancake tumbling through the void. Nothing in our solar system looks like that, but the real mystery came as it sped away. Its path could not be explained by gravity alone. It was accelerating as if pushed by an unseen force. For a comet, this is normal, caused by outgassing when sunlight vaporizes ice, creating a jet of gas that acts like a tiny rocket engine. The problem was, Oumuamua showed no visible coma, the glowing cloud of gas and dust that surrounds a comet's nucleus. It was dark, inert, and seemingly solid. This missing coma sparked a firestorm of speculation. Harvard astronomer Dr. Avi Loeb made the provocative case that Oumuamua's acceleration and strange shape were consistent with a light sail, a piece of advanced alien technology using the pressure of starlight for propulsion. He argued we should at least consider the possibility that we were looking at a discarded piece of an extraterrestrial vessel. The mainstream scientific community pushed back, proposing more natural explanations. The leading theory suggests Oumuamua was a shard of hydrogen ice. As it neared the sun, the heat would have caused the solid hydrogen to vaporize, providing the thrust for its acceleration without producing a visible dust cloud, as hydrogen gas is transparent. Another idea is that it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and lightweight that pressure from the solar wind could have pushed it along. The tragedy of Oumuamua is that we discovered it as it was already leaving. We had only a few weeks to study it before it vanished into the darkness, a fleeting enigma that left more questions than answers. Its uniqueness was underscored just 2 years later with the arrival of the second interstellar visitor, 2I Borisov. This object behaved exactly as expected, displaying a prominent coma and a clear cometary tail. It was a textbook example of an interstellar comet, making Oumuamua seem even more like an oddity. This pair of visitors opens a new chapter in astronomy. They are the first pieces of debris from other planetary systems to land on our cosmic doorstep, offering a tantalizing, direct sample of worlds orbiting other stars. How many more are drifting through the void between stars, dark and silent, passing through our solar system completely unnoticed? Each one is a fossil from an alien solar system, and their varied forms hint at the incredible diversity of planetary formation across the galaxy. This cosmic material exchange connects our local neighborhood to the vast processes of the entire Milky Way, a silent traffic of ancient rocks and ice that has been ongoing for billions of years. Two different cosmic clocks are ticking, and they stubbornly refuse to agree. This is the Hubble Tension, a growing crack in the foundation of modern cosmology. On one side, we have the ancient echo of the Big Bang itself. The Planck satellite meticulously mapped the cosmic microwave background, the faint afterglow from when the universe was just 380,000 years old. By analyzing the subtle ripples in this primordial light, scientists can extrapolate forward, calculating how fast the universe should be expanding today. This method gives us a Hubble constant of about 67 kilometers per second per megaparsec. Think of this as a cosmic speed limit, meaning that for every megaparsec, about 3.3 million light-years, a galaxy is moving away from us 67 kilometers per second faster. On the other side, we have the local, modern universe. Astronomers use what they call the cosmic distance ladder, a series of overlapping techniques to measure how far away nearby galaxies are and how fast they are receding. They use pulsating stars called Cepheid variables, whose intrinsic brightness is tied to their pulse rate, and brilliant Type 1, a supernova, which all explode with the same peak brightness. These local measurements consistently yield a faster expansion rate, around 73 kilometers per second per megaparsec. The universe today appears to be expanding significantly faster than the ancient light says it should be. This is not a small margin of error. It is a persistent and significant gap that has survived over a decade of increasingly precise observations. Renowned cosmologist Dr. Wendy Friedman has dedicated her career to refining these local measurements, cross-checking Cepheids with other methods to rule out systematic errors, and the tension only tightens. So what does this discrepancy mean? If it is not a hidden error in our measurements, then we are likely missing a crucial piece of physics. Perhaps dark energy, the force driving cosmic acceleration, is not constant as we assumed. Maybe it has been strengthening over time, giving the expansion an extra push that our models did not account for. Or it could point to exotic, unknown types of neutrinos, ghostly particles that stream through the universe, subtly altering its expansion history. Some theorists even suggest this is a sign that Einstein's theory of gravity itself needs a slight modification when applied to the cosmos as a whole. This conflict forces us to question the very parameters we use to describe reality, the fundamental ingredients and rules of the standard model of cosmology. The Hubble tension is more than a statistical anomaly. It is a direct challenge, a cosmic clue that our understanding of the universe's evolution from its first breath to the present day is fundamentally incomplete. What new physics must we invent to make these two clocks tell the same time? A question that pulls us back toward the universe's very first moment. This single, perfect alignment rattles the very foundation of modern cosmology. Deep within the faint, cold glow of the cosmic microwave background, the afterglow of the Big Bang itself, there appears to be a preferred direction in the cosmos, a shadowy imprint that scientists have grimly nicknamed the axis of evil. The cosmological principle, a cornerstone of our understanding, insists the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction, with no central point and no meaningful orientation. The axis of evil suggests we might be wrong. The anomaly first emerged clearly in data from the Wilkinson Microwave Anisotropy Probe, or WMAP, and it stubbornly persisted in the even more precise measurements from the Planck satellite. It is not a single feature, but a strange statistical alignment in the multipole moments of the radiation. Think of these multipoles as the different harmonics of the universe's first light, much like the different notes that make up a musical chord. In a truly random, isotropic universe, these notes should be uncorrelated, playing independently. Instead, some of the largest scale patterns, the lowest notes in this cosmic chord, appear to be aligned with the plane of our own solar system and the direction we are moving through space. The probability of this happening by pure chance is incredibly low. Physicist Dr. Kate Land was among those who rigorously analyzed this data, co-authoring papers that asked whether this was just a monumental fluke or something far more profound. She and her colleagues had to confront the unsettling possibility that this alignment might be real, a fossil from a time before the Big Bang. Could the universe we see have been born with a fundamental orientation, its initial conditions imprinted with a structure that breaks the sacred cosmological principle? One radical theory suggests our universe is not all there is, that it may have collided with another universe in the multiverse in its earliest moments, leaving a bruise on the cosmic microwave background. Another idea posits that the fabric of spacetime itself might be slightly anisotropic, stretching differently in one direction than in others, like a piece of fabric with a subtle grain. If the axis of evil is not a statistical illusion, it forces a humbling conclusion that our position in the cosmos is not entirely random or average. It hints that we may, in some small way, be special, living at a location that is aligned with the universe's deepest architecture. This single, ghostly axis challenges the Copernican principle we hold so dear, the idea that we do not occupy a privileged place. What other fundamental assumptions about reality are based on a cosmic uniformity that might not exist? The unsettling idea of a preferred cosmic axis forces us to question the very nature of our existence, but a deeper paradox challenges whether we exist at all. What if your consciousness, your memories, and your entire perception of reality are not the product of 14 billion years of cosmic evolution, but merely a fleeting, random accident? This is the chilling thought experiment of the Boltzmann brain. It begins with the second law of thermodynamics and the concept of entropy, the universe's tendency toward disorder. In the 19th century, physicist Ludwig Boltzmann proposed a radical idea to explain why we see a universe moving from order to chaos. He suggested that our entire ordered cosmos, with its galaxies and civilizations, might itself be a rare but inevitable statistical fluctuation within a much larger, eternal, and almost entirely random void. In an infinite or near-infinite universe, every possible arrangement of particles, no matter how improbable, will eventually occur by random chance. Given enough time, the random jostling of atoms in the void could spontaneously assemble a fully formed, self-aware brain, complete with false memories of a past that never happened, hallucinating a consistent reality around it. The statistics are mind-numbing. The probability of a single, isolated brain popping into existence from a quantum fluctuation is astronomically low, but it is still vastly more likely than the spontaneous formation of an entire, ordered universe spanning billions of light years. The math seems to suggest that in a truly eternal cosmos, Boltzmann brains should outnumber ordinary, evolved minds like ours by an unimaginable factor. So why do we find ourselves as part of a vast, coherent universe, and not as lonely, disembodied minds floating in the void? This is the core of the paradox, a profound conflict between cosmology and common sense. Modern physicists like Dr. Sean Carroll grapple with this directly. In the context of eternal inflation, where pocket universes constantly bud off from a larger multiverse, the conditions for Boltzmann brains could be rampant. If our universe continues expanding forever, destined for a cold, empty heat death, then the time available for random fluctuations is essentially infinite. Over trillions upon trillions of years, the formation of these phantom minds becomes not just possible but inevitable. This leads directly to the anthropic principle. Perhaps the only reason we observe an ordered universe is that disordered realities cannot support conscious observers to witness them. We could not be a Boltzmann brain because such an entity would be a momentary glitch, instantly dissolving back into chaos, unable to form a stable, consistent world. Our very existence as persistent observers who remember a past and anticipate a future selectively rules out the most random possibilities. Yet the paradox remains a sharp thorn in the side of our best cosmological models. If a theory predicts that most conscious experiences are these random, disembodied hallucinations, then that theory is likely flawed. The Boltzmann brain forces us to confront the nature of consciousness itself. Are we just a collection of atoms arranged in a specific pattern? And if so, could that pattern not form in a trillion other ways? This philosophical puzzle suggests that the greatest cosmic mystery may not be out in the distant galaxies, but locked within the very act of perception, a fragile flicker of awareness in a silent, statistical abyss. This profound uncertainty about our own consciousness finds a startling echo in a modern idea, the the suggestion that our universe might be a digital fabrication. The simulation hypothesis proposes that everything we perceive, from the farthest galaxy to the feeling of warmth on your skin, is not the fundamental reality but an elaborate simulation, a universe running on some advanced civilization's computer. Philosopher Nick Bostrom formalized this trippy concept, arguing that if a civilization ever reaches a post-human stage capable of running vast numbers of ancestor simulations, then the vast majority of conscious minds would not be made of flesh and blood, but of code. Statistically, we are far more likely to be one of those simulated beings than an original one in the base reality. This is not just a plot from a science fiction movie. Figures like Elon Musk have pointed to the incredible, exponential progress in our own computing and video game graphics. Within a few decades, we have gone from simple pixels to immersive virtual worlds. If this trend continues for centuries or millennia, the creation of a reality indistinguishable from our own seems not just possible but inevitable. The argument rests on probability. If even a tiny fraction of advanced civilizations run such simulations, the number of simulated universes would vastly outnumber the one real one. Therefore, the odds are overwhelmingly high that we are living inside a simulation right now. But could we ever find proof, a glitch in the matrix? Some have looked for potential evidence in the very laws of physics. The finite speed of light could be seen as a processing limit, a refresh rate for the simulation. The strange quantum nature of reality, where particles exist in fuzzy superpositions until observed, resembles a computer program that only renders the details of a scene when someone is looking at it, a technique used in video game design to conserve processing power. Yet this idea faces fierce criticism. Many scientists, like physicist Neil deGrasse Tyson, point out that the hypothesis is currently unfalsifiable, meaning there is no conceivable experiment that could prove it wrong. Any evidence we might find, any supposed glitch, could simply be explained as a feature of the base reality's laws. Furthermore, the computational power required to simulate every particle in a universe is mind-boggling, perhaps physically impossible even for an advanced civilization. But the true power of the simulation hypothesis is not in proving it true, but in the profound philosophical questions it forces us to ask. If we are in a simulation, then the laws of physics are not fundamental truths, but merely the programmed rules of the system. Consciousness is not an emergent property of biology, but a type of data that can be instantiated in a machine. The very nature of existence becomes negotiable. This modern digital myth challenges us in the same way ancient creation stories did, inviting us to look at the fabric of the cosmos and wonder if we are the creators, the created, or simply characters in a story whose author we will never meet. The idea that our universe is a simulation finds a strange parallel in a concept that is even more expansive, the multiverse. This is not a single, grand reality, but an infinite ensemble of them, a cosmic tapestry where every possible set of physical laws and constants is realized somewhere. In this view, our universe, with its stars, planets, and life, is not special. It is merely one page in an infinite library of realities. The concept emerges naturally from our most advanced theories of physics. The theory of eternal inflation suggests that the rapid expansion of the Big Bang never truly stopped, but continues forever in a background space. Within this inflating foam, pockets constantly pinch off to form isolated bubble universes, each with its own unique properties. String theory, a candidate for a theory of everything, proposes a vast landscape of possible vacuum states, each corresponding to a different universe with different dimensions and forces. Even the quantum many-worlds interpretation argues that every quantum decision spawns a new, branching reality, creating an ever-expanding tree of parallel existences. Cosmologist Dr. Max Tegmark has brought a powerful structure to this dizzying idea, categorizing multiverses into 4 distinct levels. The first level is simply space beyond our cosmic horizon, regions so far away their light has not had time to reach us. The second level involves those other bubble universes from eternal inflation, with genuinely different physical laws. The third is the many worlds of quantum mechanics, and the fourth is the ultimate ensemble, where even the mathematical rules themselves are different. This framework helps us grasp the sheer scale of what might be out there. The multiverse offers a powerful, if controversial, answer to one of cosmology's deepest puzzles, the fine-tuning of the universe. Why do the fundamental constants, like the strength of gravity or the mass of an electron, seem perfectly calibrated to allow for the existence of stars, planets, and life? If even one constant were slightly different, carbon could not form, and the universe would be sterile. In a multiverse, there is no mystery. We simply live in one of the rare universes where the numbers randomly came out right for us to exist. This is the anthropic principle on a cosmic scale, yet this elegant solution comes with a profound cost. If other universes are permanently beyond our reach, causally disconnected from our own, then the multiverse theory may be fundamentally untestable. How can we prove the existence of something we can never observe or interact with? This pushes science to its very limits, blurring the line between empirical physics and philosophical speculation. Some theorists search for potential scars on our cosmos, the imprint of a collision with another bubble universe in the ancient past, perhaps hidden in the pattern of the cosmic microwave background. Others suggest that the mysterious dark flow, the coordinated motion of distant galaxy clusters, could be a gravitational tug from a neighboring reality. The multiverse stretches our definition of reality to the breaking point, forcing us to ask if science can ever comprehend a cosmos where most of existence is, by its very nature, hidden from us forever. This confrontation with the ultimate horizon of knowledge leads us to a final, fundamental boundary, one that defines the very limits of what we can ever know. Our cosmic horizon is a prison of light and time. We are surrounded by a boundary we can never cross, a final frontier defining the observable universe. This is not a physical wall, but a limit set by the finite speed of light and the age of the cosmos. Light from galaxies beyond this horizon simply has not had time to reach us in the nearly 14 billion years since the Big Bang. We are living inside a bubble of visibility, a cosmic visual sphere, and everything outside is forever hidden from our view. Astronomer Dr. Janna Levin offers a powerful way to picture this, describing our position as the center of a sphere defined not by space but by time. The edge of our sight is the moment the universe became transparent, a wall of primordial light that marks our ultimate horizon. This creates 2 distinct but equally profound boundaries. Particle horizon marks the maximum distance from which particles, including photons of light, could have possibly reached us. It is the frontier of all we have ever been able to see. Then there is the event horizon, a consequence of the universe's accelerating expansion. As dark energy pushes galaxies apart ever faster, there will come a time for each distant galaxy when its light can no longer fight against the stretching of space to reach us. It will simply fade from our sky, its image red shifting into nothingness. Over trillions of years, the observable universe will shrink to a lonely island of a few gravitationally bound galaxies, the rest having vanished beyond an unreachable edge. This isolation leads to one of the most radical ideas in theoretical physics, the holographic principle. It suggests that all the information needed to describe our 3-dimensional universe, every star, planet, and person, could be encoded on the two-dimensional surface of its boundary, like a cosmic DVD. Our rich reality might be a projection from the data stored on this ultimate horizon. This forces a humbling admission that our entire scientific understanding of the cosmos is based on a tiny, biased sample. We can only study what the light has delivered to our doorstep. What lies beyond is pure speculation, a realm that could contain infinite other universes, or structures so alien we lack the words to describe them. Are there other bubbles of reality, other cosmic horizons, each with their own laws of physics and their own observers staring out at their own limited sky? This fundamental limit to our vision forces a shift in our quest for knowledge, turning our attention back to the phenomena within our reach that continue to defy all explanation, challenging us to decipher the universe from our small, isolated corner of the stage. The very act of looking can freeze reality in its tracks. A quantum system on the verge of change can be held in a perpetual state of suspended animation, not by any physical force, but by the relentless gaze of measurement itself. This is the quantum Zeno effect, a bizarre phenomenon where a watched pot not only never boils, it never even gets warm. The name is a nod to the ancient Greek philosopher Zeno, who crafted paradoxes about an arrow that could never reach its target because its flight was an infinite series of frozen moments. In the quantum world, this philosophical puzzle becomes a startling reality. The mathematics behind it stems from Schrödinger's equation, which describes how a quantum state evolves smoothly over time like a spreading wave. But the instant you measure it, this wave function collapses, pinning the system to a single, definite state. If you measure it again almost immediately, the wave has barely had any time to spread, so it collapses right back to nearly the same state. Repeat this process rapidly and continuously, and you effectively lock the system in place, preventing it from evolving. It is like constantly asking a spinning coin if it is heads or tails, never giving it a chance to complete a full rotation. Physicist Dr. Wayne Itano and his team provided one of the first clear experimental verifications of this in the 1990s. They used a group of beryllium ions trapped in a magnetic field. These ions, when excited by a laser, would naturally decay back to their ground state. But when the researchers repeatedly observed the ions with a quick pulse of light, they found the decay was dramatically slowed. The more they looked, the more they froze the ions in their excited state. This is not just a laboratory curiosity, it has profound practical implications. The atomic clocks that govern global positioning systems and the Internet rely on the incredibly stable vibrations of atoms. The precision of these clocks is maintained, in part, by a process akin to the quantum Zeno effect, where frequent measurements help keep the atoms in a coherent state, preventing them from drifting. In the burgeoning field of quantum computing, this effect is a double-edged sword. It can be a nuisance, as unwanted observation from the environment can disrupt fragile quantum calculations, a problem known as decoherence. But researchers are also learning to harness it, using deliberate, frequent measurements to protect a quantum bit or qubit from decaying and losing its information, effectively using observation as a shield. This forces us to confront one of the deepest questions in all of physics. What constitutes a measurement? Is it the click of a detector, the interaction with a single photon, or does it require a conscious observer? The quantum Zeno effect blurs the line between the observer and the observed, suggesting that our interaction with the world is not a passive recording of events, but an active participation that shapes the very outcome. If simply watching something can alter its fundamental behavior, then what does that say about the nature of a reality that seems to exist independently of us? This quantum curiosity elevates observation from a simple act of seeing to a potential force of creation, a power that might be woven into the fabric of the cosmos itself. Observation alone seems to shape the quantum world, but what if the observer is the universe itself? The hard problem of consciousness asks why the intricate electrical storms in our brains are accompanied by a vivid, private, inner world of sensation, thought, and feeling. Why is there an experience of the color red or the taste of salt, instead of just a complex biological machine processing data in the dark? Philosopher David Chalmers framed this profound distinction, separating the easy problems of explaining cognitive functions from the truly hard problem, explaining why and how we have subjective experience at all. This is not just a puzzle for biologists, it strikes at the heart of cosmology. The standard materialist view holds that consciousness is an emergent property, a byproduct of sufficiently complex computation in the neural networks of the brain. But this leaves a glaring gap. How does mere matter, no matter how intricately arranged, suddenly spark into the light of awareness? It is like trying to explain how a whirlpool in a river suddenly becomes wet. The property was already there in the constituent parts. This has led to a radical alternative, panpsychism. This ancient idea, now being explored by modern scientists like neuroscientist Dr. Christoph Koch, proposes that consciousness is not something that emerges at a certain level of complexity, but is a fundamental property of the universe, as basic as mass or charge. In this view, even an electron might possess a tiny, rudimentary spark of subjective experience, a single bare feeling of existence. Of course, an electron is not thinking or feeling emotions, but it might have some infinitesimal degree of inner life. The combination of these proto-conscious entities into complex systems like a human brain could then give rise to the rich tapestry of thought and sensation we know. Dr. Koch links this to integrated information theory, which attempts to measure consciousness not by what a system is made of, but by its structure and its ability to integrate information into a unified whole. The theory suggests that any system with a sufficiently high degree of integrated information, symbolized by the Greek letter phi, has some level of consciousness. This could apply to a brain, a sophisticated computer network, or perhaps even the cosmos itself. This leads to a breathtaking cosmological question. If the universe is a vast, intricately connected network of information exchange, with galaxies and dark matter filaments forming a cosmic web of staggering complexity, could it possess a degree of consciousness? Is the cosmos, in some unimaginable way, self-aware? We are not talking about a bearded man in the sky, but a slow, vast, cosmic form of awareness, built from the integrated information flowing between stars and particles across billions of light years. This idea naturally intersects with quantum mechanics, where the role of the observer is so perplexing. Could it be that consciousness is not just a passive observer of quantum events, but an active participant that helps to crystallize reality from a haze of possibilities? Some interpretations of quantum theory have long pointed in this direction, suggesting that the wave function collapses only when a conscious mind observes it. While this remains highly controversial, it forces us to consider a universe where mind and cosmos are not separate, but deeply intertwined aspects of a single reality. The hard problem of consciousness ultimately dissolves the comfortable boundary between science and philosophy, challenging the materialist foundation of modern cosmology. It asks us to consider that the inner world of our minds may not be a fluke in a dead universe, but a reflection of a fundamental property woven into the fabric of spacetime itself, a silent, waiting dimension of existence we are only beginning to perceive. Our existence hinges on a broken symmetry, a single flaw in the cosmos that allowed something to emerge from nothing. In the first moments after the Big Bang, the universe was a seething cauldron of energy, constantly spawning pairs of particles and their antimatter twins. For every quark of matter, an antiquark was born. Matter and antimatter are perfect mirror images, destined to annihilate each other upon contact in a flash of pure energy. If the cosmos had been perfectly symmetrical, every particle would have met its antimatter counterpart, and the entire universe would have dissolved back into a featureless sea of radiation. There would be no stars, no planets, and certainly no one to wonder why. Yet here we are in a universe dominated by matter, with antimatter seeming to have all but vanished. This is the profound puzzle of baryon asymmetry, one of the most urgent questions in all of physics. How did a universe born with equal parts matter and antimatter end up with almost none of the latter? The answer required a set of very specific conditions, first articulated by the physicist Andrei Sakharov. He proposed 3 essential criteria for matter to gain the upper hand. The universe had to be out of thermal equilibrium, allowing processes to run one way and not simply reverse. It needed interactions that violate the conservation of baryon number, essentially allowing more matter to be created than destroyed. And most crucially, it required a violation of CP symmetry. CP stands for charge and parity. Imagine a particle and its antimatter counterpart, then view them in a mirror. If CP symmetry holds, the physics should look identical. But if it is violated, the mirror image behaves differently, providing a possible mechanism to favor matter over antimatter. We have indeed observed CP violation in certain rare particle decays, most famously in quarks. The work of particle physicist Dr. Helen Quinn has been pivotal in understanding how these symmetries might break. However, the amount of CP violation we have measured in laboratories is far too feeble to account for the overwhelming dominance of matter we see in the cosmos. It is like finding a single drop of water when you need to fill an ocean. This discrepancy sends physicists on a hunt for new, more powerful sources of this symmetry breaking. At laboratories like CERN, scientists are scrutinizing the behavior of exotic particles, such as neutrinos, to see if they hold the key. One compelling theory is leptogenesis, which suggests that the asymmetry might have originated in the neutrino sector. In this scenario, heavy, sterile neutrinos in the early universe would have decayed asymmetrically, producing more matter particles than antimatter. This lepton asymmetry could then have been converted into the baryon asymmetry we see today through subtle processes in the electroweak force. Every atom in our bodies, every star in the sky, is a relic of that primordial imbalance. The very fact that we are here to ponder this question is direct proof that the laws of physics are not perfectly symmetrical. They contain a tiny, built-in bias, a 1 in a billion preference for matter that made all the difference. Why does anything exist at all? The answer lies in a broken mirror at the dawn of time, a fundamental lopsidedness that allowed a universe of structure and life to form from an initial state of perfect balance. This incredible fine-tuning, where a slight deviation from symmetry built everything we know, forces us to confront an even deeper cosmic coincidence. The universe runs on numbers, and a slight change to any one of them would render everything you know impossible. This is the fine-tuning problem, a cosmic puzzle that asks why the fundamental constants of nature seem perfectly calibrated for life. Alter the strength of gravity by just 1 part in 10 to the 40th power, and stars would either fail to ignite or burn out in a cosmic flash, never allowing planets to form or life to evolve. Tweak the mass of a neutron by a fraction, and the stable atoms that build our world could not exist. The cosmos appears to be balanced on a razor's edge. Physicist Dr. Martin Rees famously explored this in his book Just 6 Numbers. highlighting the delicate ratios that govern everything from the nuclear forces binding atoms to the expansion rate of the universe itself. Consider the cosmological constant, the value that describes the strength of dark energy. If it were slightly larger, the universe would have blown itself apart before galaxies could ever form. If it were slightly smaller, gravity would have caused a catastrophic collapse long ago. The strong nuclear force, which glues protons and neutrons together inside atomic nuclei, is another prime example. If it were just a few percent stronger, all the hydrogen in the early universe would have fused into helium, leaving no water and no fuel for stars. If it were slightly weaker, complex elements like carbon and oxygen, the very building blocks of life, would never have been forged in stellar furnaces. We are here because these numbers landed within an extraordinarily narrow range of possibility. How do we explain this incredible luck? One answer is the anthropic principle, a logical but somewhat tautological explanation. It simply states that we observe a universe capable of supporting life because, well, we are here to observe it. In an infinite variety of universes, we necessarily find ourselves in one of the rare ones where the constants allow for our existence. This idea finds its most powerful expression in the multiverse theory. If a vast ensemble of universes exists, each with its own randomly selected set of physical laws, then our surprisingly hospitable cosmos is no longer a statistical miracle, but an inevitable outcome. We are simply the winners of a cosmic lottery. Others find this explanation unsatisfying, pointing toward the possibility of a deeper, underlying theory that dictates these values, or even, though it is a far more controversial idea, some form of cosmic design. The fine-tuning problem forces us to confront the deepest questions of purpose and chance. Are we the product of a meaningless, random fluke in an infinite cosmic landscape? Or does our existence point to a deeper layer of order woven into the fabric of reality? This profound puzzle over why the numbers are just right leads us to the final, and perhaps most fundamental, challenge to our perception of everything. This relentless acceleration could one day tear the very fabric of reality apart. The Big Rip is a final, violent destiny for the cosmos, driven by a hypothetical form of dark energy so potent it is called phantom energy. Unlike the dark energy we currently observe, phantom energy would possess an equation of state with a value less than -1. This is not just a small mathematical difference, it is a fundamental shift in behavior. Instead of a constant pressure pushing galaxies apart, phantom energy's repulsive force would grow stronger over time, becoming infinite. The expansion of the universe would not just continue, it would run away uncontrollably, overwhelming every force that holds existence together. Proposed by theoretical physicist Dr. Robert Caldwell and his colleagues, this scenario takes our current observations of cosmic acceleration and follows them to their most extreme, logical conclusion. The end would not come all at once, but in a terrifying, sequenced unraveling. Roughly 60 million years before the final moment, the phantom energy's grip would become strong enough to overcome gravity's hold. First, our local group of galaxies, including Andromeda and the Milky Way, which are destined to merge, would be torn asunder. Galaxies would fly apart into the growing void. Then, about 3 months before the end, the phantom force would rip apart our own Milky Way. Stars would be flung into the darkness, their light fading as the space between them stretched faster than light itself. With just minutes to go, the solar system would be shredded. The sun's gravity would be useless against the cosmic tide, and planets would be torn from their orbits. In the final, catastrophic moments, the forces that bind matter itself would fail. About an atom's width from the end, planets and stars would be ripped apart. In the last unimaginable fraction of a second, atoms and atomic nuclei would be shredded. Space-time itself would be torn asunder, dissolving the very stage upon which the universe plays out. This is not the favored model, as current data suggests dark energy behaves like a cosmological constant. But the mere possibility of phantom energy highlights a profound uncertainty at the heart of cosmology. We do not yet know the true nature of the force that dominates our universe, and its future behavior remains the greatest mystery. This ultimate fate challenges our deepest concepts of eternity and nothingness, forcing us to confront a cosmos that could end not with a whimper, but with a scream that tears down the pillars of reality itself. For thousands of years, we have looked to the stars and told stories to explain their mysteries. Ancient civilizations saw not distant suns, but gods and heroes painted across the celestial sphere. The universe was a small, intimate place with Earth firmly at its center. This geocentric view was a comforting lie, a story that placed humanity at the heart of creation. The first crack in this cosmic egg came from a handful of brave thinkers who dared to trust their eyes over ancient dogma. Galileo Galilei, pointing his crude telescope at the heavens, saw moons orbiting Jupiter and the phases of Venus, evidence that not everything revolved around us. For this heresy, he was forced to recant, but the truth could not be imprisoned. The universe had been pried open, and our world was cast adrift from its privileged position, just one world among many. This was more than a scientific correction. It was a psychological earthquake that redefined our place in the cosmos. The mystery then shifted from the arrangement of our solar system to the nature of the stars themselves. Those faint, fuzzy patches of light known as nebulae were long thought to be clouds within our own Milky Way. Then, in the 1920s, Edwin Hubble, using the powerful new Hooker telescope, identified individual stars within the Andromeda Nebula. He calculated its staggering distance, proving it was an island universe entirely separate from our own. The cosmos exploded in size overnight, becoming a vast ocean of galaxies, each with billions of suns. Hubble made another discovery that was even more profound. By analyzing the light from these galaxies, he found that almost all of them were flying away from us, their light stretched to redder wavelengths. The universe was not static, it was expanding, fleeing from itself in a grand, cosmic exodus. This observation pointed directly backward in time to a singular origin, the moment we now call the Big Bang. Each of these revolutions was met with resistance, not from a lack of evidence, but from a deep-seated reluctance to abandon a comfortable reality for a more wondrous and often more humbling truth. Our journey from a small, Earth-centered universe to an expanding cosmos of dark energy and invisible matter is a story of shattered paradigms. The very questions we ask today about dark matter and quantum realms would have been incomprehensible to Galileo or Hubble. This historical perspective is crucial because it frames our current puzzles not as final failures, but as the latest chapter in an endless story of discovery. The mysteries that challenge us now, from the Great Attractor to the holographic principle, are simply the new horizon. Future generations will likely look back at our certainty about dark energy or the Big Bang with the same gentle astonishment we now feel for the celestial spheres. They will have their own revolutions built upon the foundations we are laying today. This continuous unfolding of understanding is the true nature of scientific inquiry, a perpetual journey where every answer reveals a deeper, more beautiful question. These cosmic riddles, from the ghostly pull of dark matter to the phantom menace of a final rip, all point to a single humbling truth: our map of reality is forever unfinished. Each mystery we have explored does more than just challenge a theory. It shatters a comfortable assumption and forces us to redraw the boundaries of the possible. This is not a failure of science, but its very engine, a perpetual cycle of question, discovery, and deeper wonder. The late, great Carl Sagan once reflected that the cosmos is within us. We are made of star stuff. Every atom in your body was forged in the heart of a long-dead star, catapulted across space by ancient explosions to eventually become part of you. A conscious being capable of looking back at the universe and questioning its nature. This journey through the universe's strangest corners is an invitation to carry that sense of awe into your daily life. The next time you find yourself under a clear night sky, look up. Let your eyes adjust to the depth. Those points of light are not just pretty specks, they are suns, galaxies, and cosmic mysteries waiting to be unraveled. Think of the invisible matter weaving the galaxies together, the spooky connection of distant particles, and the silent, accelerating push that defines our ultimate fate. We want to hear which of these phenomena made you question reality the most, so share your thoughts in the comments below. If this voyage into the unknown expanded your perception of the cosmos, consider subscribing for more journeys to the edges of understanding. The universe is vast, mysterious, and it is waiting for you to explore.